Hello girls, how are you? Today we want to start with our last chapter for this semester, chapter 33, Sound Waves. Okay, now we talked about waves a lot. We talked about light waves. Now we want to start to talk about sound waves. The first thing I want you to know it about sound waves is what? That sound waves, they are longitudinal waves. Till now, we didn't talk about longitudinal waves. All the waves that we talked about before, they were what? Transverse wave. So, to remember transverse wave, here is a transverse wave. Transverse wave, it is the wave that the particles of the medium, the vibrations of the particles of the medium, the particles, they move up and down, but the direction of the motion of the wave is forward. Now, in a longitudinal wave, we don't have this case. What do we have? The particles of the medium, they move backward and forward, back and forth, back and forth all the time. So here, for example, look how they are moving backward and forward. So they are parallel to the direction of motion of the wave. They are moving the same direction as the direction of the wave. The particles and the direction of the wave, the same direction. Okay, this is the first thing about longitudinal waves. The second thing in longitudinal waves that we have some area or parts of the wave, we call this part what? Compression, and another one we call it rarefaction. What's the difference between them? Compression is when the particles, they are close to each other. Look, the particles of the medium, when they are close to each other, this area we call it compression. In the case where the particles are away from each other, it's the same as here. And here, this we call it rarefactions. Okay? So, longitudinal wave vibrations of the medium occur in the same direction as the wave movement. Now, look here. This is what? A spring. We form a longitudinal wave by a spring. To understand compressions and rarefactions, look here, where the coils are closer together, like this area, what do we call this thing? Compression. Where the coils are further apart, this is a rarefaction. Okay? The second thing, look here at this case. If we draw them as lines, parallel lines, where the lines are close to each other, compression. Where the lines are further apart, rarefaction. You have to know all ways of drawing sound waves because they ask you in paper 4 to draw sound waves, okay? Good. Now, the number of compressions produced per second is the frequency of the sound wave. Look here, please, at this figure. Do you remember frequency? It's the number of compressions produced per second. Here, in this case, with a sound wave, it's the number of compressions, okay? So here, how many compressions we have? Let's compare between this one and this one. Now here I have what? 3 compressions per second. Here I have more than 3. So what do you understand? Here I have high frequency. Here I have low frequency. So if they ask you which one has higher frequency than the other, how do you know? You just count the number of compressions per second. Compression, compression, compression. Look here, we have more compression than here. This is the frequency. The distance between successive compressions is the wavelength. You remember the wavelength? Here's the wavelength here. The distance between one compression to the other. Most of the time, we take it from the middle of the compression. For example, here, you take it, here's the compression, from the middle of this one to the middle of this one. Here is the wavelength, okay? From the middle of the first compression to the middle of the second compression, okay? Also, longitudinal waves, we use the wave formula, which is speed equals frequency times wavelength. Okay? It's very important to know what does it mean, high frequency and low frequency, long wavelength, short wavelength in sound waves, okay, in longitudinal waves. Great. So, again, we said sound waves. It's a type of longitudinal wave. It has compressions and rarefactions. Compressions, regions where the vibrating particles are closest together, the same as here and here and here, and rarefactions, regions where the particles are furthest apart, the same as these areas. Vibrations that pass through the molecules of a medium, this is the direction of the vibrations of the particles through the medium. Okay? Great. Now, girls, it is very easy to create sound, right? For example, now I'm talking to you at this moment and you can hear me by your speakers. So, your speakers making the sound. So, how? Your speakers, they what? They vibrate, so they cause the air that is close to them to vibrate. So the air particles start to vibrate. Then what happens until these waves reach your ears? Okay, so what do we need to sound? Sound waves come from a vibrating source. We want something to vibrate. When something vibrates, it means that there is sound. Examples: a guitar has strings. Now this guitar has strings, so they vibrate. This is the source of sound here. The drum has a stretched skin, so the stretched skin vibrate. It causes the air to vibrate, sound produced. The human voice has vocal cords. Now we have vocal cords, also they vibrate. That's why sound produced. Okay? So, let's watch here this video together, then we'll continue.
State again, energy is traveling across the room here, but air itself is not traveling across the room. Only the disturbance within the air is traveling across the room. If air were being transported across the room, it'd be better characterized not as sound, but as wind. So this is why we call sound a sound wave, because it shares the defining feature of waves, which is being able to transport energy through a medium without having to transport the medium itself.
Okay, here we have a very important note. Now, girls, what happens exactly? Look here. Now, speakers, what do they have? The speaker has a cone, which is made to vibrate in and out by an electric current. When the cone moves out, the air in front is compressed. When it moves in, the air is rarefied, so it goes thinner. The wave progresses through the air, but the air as a whole doesn't move. Okay, so energy only moves, but the air particles, they don't move. Here, the particles that are here will stay here. They will just send the energy or the vibrations to the other particles and so on. Okay, so waves can transport energy through a medium without transporting the medium itself. As sound waves progresses through a medium, they cause the particles to move closer together. Okay, sounds need medium to travel through. It cannot pass through vacuum or space. It's very important. Most of the time in paper 2 or paper 4 they ask this question. Why sound waves cannot pass through vacuum or space? The reason is what? Because sound waves need medium to travel through. In space we don't have matter, we don't have medium. So how What's the thing that will vibrate there? Nothing. That's why it's not the same as light. You remember light waves? They can pass through medium or space. Sound? No. Okay, because there is no medium or matter to travel for the sound wave to travel through. Okay. Now, how human hearing works. Now, we talked how sound produced. Now, how human hearing works. When the wave enters your ear, okay, compressions and rarefactions cause small, rapid pressure changes of the eardrum. This small part of the ear starts to vibrate after the waves enter the ear. So when the eardrum starts to vibrate, it causes this internal part also to vibrate, and you experience the sensation of sound. That's it. That's what I want you to know about human hearing. Okay? Now, vibrations can be at any frequency. Now, any vibration, it can be at any frequency. But we, as humans, we can hear only sounds with a frequency between 20 hertz to 20,000 hertz only. Now, only this is the range from 20 hertz to 20,000 hertz. Some animals have range above this called ultrasounds, okay? They can be heard by bats and dogs. And some animals, like whales, for example, they use subsonics less than 20 hertz sound frequency to communicate over long distances. But we can't hear these four sounds. We only hear sounds, the frequency between 20 hertz to 20,000 hertz. Okay, different people have slightly different hearing ranges, and as we get older, the range of our hearing normally decreases. Is that clear? Okay, that's all for today, girls. Tomorrow we will continue our lesson. Thank you.